the way you keep interested in things. When you get older, that gets very frustrating because you know you've got all these projects and you don't know how you're going to end them. There are things like the Epsilon Aurigae system. Secondary eclipse should be happening right about now. Nobody's going to look for it. The A38 Mon is rebrightening, and to keep following that would be an interesting thing. QX-CAS is a eclipsing binary system that no longer eclipses. And so when is it going to start eclipsing again? So monitoring that. CMOS camera studies, filter studies, the bright spectral robot with Gary Walker. So just lots of things. But I want to highlight sort of 3 things right now, 2 projects that you guys can do, and 1 project that I would like some help on. First of those, which isn't going to show up on here, is the Crab pulsar. It turns out that with a small telescope, say sort of the 12-inch variety, you can actually get a decent light curve for the Crab pulsar. A camera that does this very well is the QHY-174 GPS system, and QHY has actually loaned me one of those cameras, and so when the Crab pulsar becomes visible again, sort of late summer, I'd like to go and do that. If somebody beats me to it first, fine. I'm happy to see results show up. But if they don't, then if somebody wants to work with me on that, I'd be happy to. It's going to require some 80 to 100,000 images, so I need somebody to go and process the data. But the 2 projects that I'm going to highlight here, go to the next slide. The first one is Polaris. So, second magnitude star, right? We know everything about it, right? Next. It is the brightest classical Cepheid, second magnitude star, only 130 parsecs away, so it's also the nearest Cepheid. But notice the period, 3.97 days, so it's a difficult one to study. The period is increasing by a rate of about 316 seconds per century. That kind of rate is rare. And if you look at the O-C diagram, there was a glitch in the period that occurred around 1960, about the same time that the star started to decrease in amplitude. So back when I first started looking at the star, the amplitude was sort of 1/10 of a magnitude during the light cycle, and it's decreased to about 0.02 magnitudes, and it's about 0.03 today. The light curve itself is sinusoidal. A type of star called a sinusoidal delta Cephei star, and it's probably pulsating in the first overtone. So one of the questions is, what is its evolutionary state? It appears to be crossing the Cepheid instability strip for the first time, which is kind of a rare object in itself. Next. It's a triple system. There is Polaris AB, which is a spectroscopic binary, but it's also been visually resolved by HST. And then Polaris B itself, which is a wide visual binary about 18 arcseconds away. It's about an 8th magnitude star. There is an analog for Polaris, at least as far as sort of the decrease in amplitude and everything. HD 344787. This is about an 11th magnitude star, so it's a little bit easier to study. There are 2 main professional astronomers who have been following Polaris, and then Tom Calderwood has been doing some photoelectric photometry of the star in the recent times. So a good review paper, if you ever want to look at Polaris, is this one by Dave Turner. Next. So this is what the light curve looks like. This was 2005-ish. You can see it's just a sinusoidal, about 0.03 of a magnitude variation. Pretty difficult to do at second magnitude star. These are all from satellite observations. Next. This is Tom Calderwood's light curve for the most part. I don't think there's anybody else in here. He does V and I, plus with the SSB4, he can do J and H as well. It's a very difficult star. You can see the amplitude is very small. Next. So how do you observe Polaris? Well, everybody knows you can see it all the time, at least from the northern hemisphere. It does have one brightish star that's about 45 arc minutes away at a magnitude of V of 6.4. And then the main comp star that the photoelectric observers have been using is about 3 degrees away, a magnitude of 4. So those are your two main comp stars that you can use. If you're using a CCD system, you'd probably use the 6th magnitude star because it's really close. You can sort of get it in your field of view. If you're using a DSLR or something like that, then you might want to do something with a wider field, and you can use the star that's closer in magnitude. It's bright, so you can actually observe it during the daytime. And so that's one way of breaking that 3.97 day period, is just observe it 24 hours. And you can do that from any site. And then if you want to do transformations so that you actually can have your light curve, compare it with somebody else, you need to do it in 2 filters. But at least it has a 4-day period. You can do 2 filters and just cycle through them, and no big problem. Next. Here's a 1-degree finding chart. You can see with that nearby star 6.47, so 6.5 magnitude. Down to the lower right, there's a couple other stars that you could use for check stars or something like that in the field of view. It's a pretty sparse field of view. Next. Next slide. And the main thing you're going to run into if you do any observation for this is that you have to do very short exposures with a CCD system. Typically something like 0.01 seconds is what you need. And so you got to stack a whole bunch of these in order to beat down scintillation. And so it's a project where it sounds simple, but it's actually complex. Because if you start taking a lot of 20 megabyte images and stacking several thousand of them, it adds up in a big hurry. You don't necessarily have to track. So it's a good project for a telescope that you just have in storage, you know, your little 3-inch refractor, your CCD system that you're no longer using because you have this nice, wonderful CMOS system. Just put them out, have them monitor Polaris. And so you can do it even without a tracking system. Next. The visual companion is about 8th magnitude, as I said. So if you're going to do this, it's nice to use an aperture that's sort of smaller than 18 or 20 arc seconds, just so that you primarily remove that nearby companion. And because it's an F8 type star, if you go to the blue, you'll get a higher amplitude. And so if you want to get something with a really nice light curve, you'd go to U or B. The period change, because it's decreasing in period, and the amplitude change means that you really want to observe it, monitor it for year after year after year. So that's why it's nice to put it on a separate little stand and just let it run and do its thing. The other thing is that you can do spectroscopy of Polaris, 2nd magnitude star, easy. The VR curve is about 10 to 20 kilometers per second. So it's a little bit on the difficult side, but not impossible for amateurs to do. So you can do a nice light curve that way as well. In this case, radial velocity curve. Next. So I'm asking people to go off and observe Polaris. Submit the data to the APASS-2. If you do so, I will be looking at that data, and I'll be happy to give you some helpful hints as to data quality and things that you might do to improve your data. So it's a nice little separate self-contained project. The bigger one is this guy, APASS. Remember that APASS has been released through data release 10, I believe it is. Yes, 910. The hope was for data release 11 to occur several years ago. It hasn't, but it turns out that I'm giving a paper at the November AAVSO meeting, and there I'm going to announce data release 11. And in order to do that, I need some help. And then the other two things that are on there, APASS-2 and XPASS, I'll talk about those in a minute. Those are extensions of APASS that are currently underway. Next. So the APASS survey itself, everybody pretty well has seen this before. It was a 5-filter survey. Primarily, the idea was 4 visits to each field, so it should beat down the noise a little bit, and sort of a 10 to 17th magnitude range. It's been funded both from the Robert Ayers Sciences Fund and NSF, and it's been used by a whole bunch of professionals as well as the amateur community. I originally did it for getting comp stars for AVSO targets, but it's been used for other things as well. Next. This is the setup in APASS North. This is at Bill Stein's house, and you can see the sort of parameters that are designed for it. It's sort of quasi-simultaneous two filters at once, a blue and a red, and using ASA N8 8-inch astrographs. Next. There's the 2 sites, APASS North, Bill Stein's place, and the APASS South, which is at CTIO in the M-Earth building. Next. This was the DR9 coverage. It's basically the same as DR10. There's a couple gaps in here, but the coverage over the sky is pretty good. Next. The first extension for APASS, which is sort of started, but it hasn't completed, is to add some additional filters. So the ones that are in yellow here, the Sloan U, along with a Z short filter and a Y filter, we have those filters in the filter wheel. You know, they've been used for a few fields, but not for everything. The idea here is to go ahead and extend it for all the fields. So it really does cover the entire range of silicon, so that whatever calibration you need, you can get. Next. Here's the operational pipeline that's currently in stage, and you can see that it's pretty complex because you not only have to do the queue scheduling, which is done through ACP, but you also have to keep track of finished fields and things like this and sort of clean the queue every now and then. The images themselves are processed locally, and then star lists are transmitted to the host facility, to our facility. The images themselves we do with SneakerNet and bring them back at some time later. And on and on. Next. Here's an idea of the fact that with any kind of a CCD or CMOS sensor, you're going to reach saturation at some point. So they're not infinitely good at bright and faint. In this case, it shows you that right around 10th magnitude plus minus, the system tends to saturate, and it's no longer a linear fit with magnitude. And this is what happens when you have an ABG type sensor. Next. Community access to the catalog itself. You can get the means catalogs, the sort of 4 average values for each position. And then you can, there actually is a way to get to the individual observations as a function of JD. And I don't think you can get to that from the AVSO webpage, but I can show you how to do it. And then if you want the whole catalog, 120 million objects or something like that, many gigabytes of data, just ask AVSO headquarters for a copy and they can get it for you. Next. So like I said, it takes a lot of people to do this kind of a survey. There's sort of 3 main astronomers who've been working on it, 3 or 4, but the rest of them are all volunteers, people who are hosting the telescope, like Bill Stein and Tom Smith before that. People who contribute various things. Don Goldman with the Astrodon filters, Bob Denning with ACP. And it's just been great working with all these people. And I'm happy to work with more. So anybody who wants to get involved in the project, I can find a spot for you. I guarantee it. Next. So here are the to-do things that are coming up. First is DR11, which is going to be released in November. I'm redoing all the transformations. I'm adding 100 nights of new data, including the 3 filters in those fields where we have them. And then I want to take a few additional observations to fill in some of the sparse fields. And then after DR11 is actually released, I want to submit a true science paper for it, so it's something that can be acknowledged. And I need volunteers for a lot of this stuff. We're going to take new data. I need people who will operate the telescopes at the various sites. So that means, starting it up at the beginning of the night, logging what kind of weather conditions are taking place, because you really want only photometric data and things like that. And then for writing the paper or stuff on the website, I need people who can create good tables and graphs that are publishable quality and things like this. I can do it, but it takes me a lot of time to do it. I'd rather somebody else take that step. Next. And then there's this follow-on stuff. Remember, APASS sort of dies at, or saturates at 10th magnitude. There was an extension that was started with NSF to bring it down to 7.5 magnitude. And that was as far as I could go with the typical shutters that were available on Apogee cameras. You start getting into shutter vignetting once you get to shorter exposures. But now we're switching over to QHY 600 cameras. And so we can take really short exposures, which means we can go to the brightest stars in the sky. And that's the intent. But in order to do that, you don't want to store 1,000 images from a QHY 600 for every object that you take through the night. So there's got to be a way of doing real-time floating point stacking of those images. And that really isn't available right now, at least through MaximDL. We're moving all the processing and storage to the cloud. And then I'm changing all the software that's written for IRAF and things like that, moving it into Python. So somebody's a really good Python programmer, come to me. Next. And so one of the things we're going to be doing is introducing a third site for APASS. This has been furnished by Wayne Rosing of Las Cumbres. He's allowing us space in the dome or the clamshell of Fox North and Haleakala in Hawaii. And he's also helping refurbish the other APASS systems. Next. So like I said, that real-time stacking type thing for MaximDL or a way of moving over to some other system, that's fine. Python updates, all the operational tasks of calibrating the images and getting transformation coefficients and everything else that we're doing for DR11 has to be done for APASS-2 or XPASS. Next. That's it. So I mentioned APASS-2 and XPASS. XPASS right now is a 12-inch telescope that's in my backyard. It's a joint project with Gary Walker. And the concept for XPASS right now is I'm just studying how to do bright stars with a telescope and to do them with high precision. And the question is can you stack very short exposures and get the same results as, say, using a neutral density filter and taking longer exposures? And so those are the kinds of issues that we're trying to resolve. And it's easier to do that in your backyard than it is 6,000 miles away. So that's why that facility has been set up as a test bed for the extended survey. Okay, so like I said, if anybody wants to get involved in APASS, your chance is now. I'll be happy to take volunteers, names on cards, whatever. All right, so that's all I have.
Okay, questions?
You mentioned that you're going to move to cloud processing. So does that mean the 20 gigabytes or whatever will be uploaded, including if you've got higher data rate, so more images per night?
It's being moved to cloud because Las Cumbres uses the cloud. And so the Haleakala node is going to be done all with cloud-based software. And the other sites like Bill Stein's place and so on will probably still at least do the image processing locally, upload the star list, and then do all the processing from there. So it's to upload 20 to 30 gigabytes of data every night is kind of problematic at some sites. And so we're trying to avoid that, except at the sites where it's really convenient to do so.
So back to Polaris, okay?
Yay, my favorite star. I started studying that in 1978.
So I'm thinking of taking a one-shot color camera, not cooled, one of the real old dogs, okay, but it's a one-shot color, but it'll oversample everything, and putting a filter wheel on it that goes between a neutral density and a non-neutral density, and dithering back and forth, so that the exposures, so that we can get more comp stars, okay, and as long as we measure the change in what would be RGB or BB whatever, in the neutral density filter. As long as we model the passband differences in the neutral density filter and dithering back and forth, does that sound like a viable way to play this game?
It is a viable way to play the game if you're talking about amplitudes that are 300ths of a magnitude. Give it a try. I mean, this is all experimental science. See what you get.
All right.
Neutral density filters aren't neutral, as you well know, and it just depends on whether or not the deviations are important for stellar type objects.
Well, the key measurement I would think that I would be making is I would compare essentially B and V using the stacked scintillated stack against the BV through the neutral density filter and make a transform specific to Polaris. Okay, and then the comps, and do the similar thing on the comp star, whether in fact by modulating the exposure time rather than the neutral density filter, and see where I end up.
Yep, sounds like a good project.
Arne, if we could go back to the slide where you had the 18 millisecond on Polaris.
18 arcsecond on Polaris.
Arcsecond. Yeah, I was confused. You talked about being able to use a small refractor.
Go back.
Or a small
go forward from there. One more.
Nope.
Nope, wasn't. I guess I'm, there it is. Yeah.
So I didn't quite understand. Best to use aperture less than 18 arcsecond diameter. Can you explain? You talked about using a small refractor. It's obviously a very bright target.
Right.
And a small refractor and more thinning camera is probably going to get field of view at least to pick up that 6.4 star, but I don't understand the aperture 18 arcsecond.
Okay, the reason for the 18 arcsecond aperture is that if you include that 8th magnitude companion in your aperture, then you dilute the amplitude. And so what you want,
aperture.
Okay, so what you want is to make that aperture small enough that the companion isn't a major effect. Yeah. But nobody studies this star. Second magnitude star. How many surveys pick up that star?
How hard is it to do with a gem, for example? I mean, it's hard. 9 and 10, if I remember, had some systematic errors, problems. How are you addressing those for 11?
They will be compared against things like Atlas, because we do have, you know, GR and I from Sloan, and so we can compare against there and see where the effects are and then model them out.
Okay.
Part of the problem is that you're dealing with a 3-degree field of view with these ASA N8s, and the geometric quality is not great. And so what happens is stars that are in the edge of field of view are distorted somewhat. And I've put in a correction to take care of that, but somebody else needs to go in and model it properly and do the correction properly. So if somebody wants to play with that aspect of it, more power to you.
So this is just to further encourage people to observe Polaris. 2 years ago, my presentation for this conference was about Betelgeuse going through a historic minimum. And what I did is took my 12.5-inch backyard telescope in the middle of the city in Phoenix, and we made aperture stop, and we defocused and did, like you say, a set of exposures that you average out to try to get rid of the scintillation effect. And the result, I mean, it's kind of redundant, but at least I was encouraged that it came pretty close to matching Tom Calderwood, who I consider, you know, that's the standard he's using, a photoelectric photometer. But it's very doable, and that's a first magnitude star, and trace the minimum out pretty well. So it can be done. And now I kind of want to try this now that you're showing this.
On correcting for the non-flat field in your scopes, have you done flux conserving resampling and flattening the field and then reconstructing it, or are you doing something other than that, or what method are you using?
The method that's currently being used is to compare the photometry in standard fields, quote standard fields that we mosaicked with the SRO telescope in Sonoida, so that we have the more correct, at least, how do you put it? The magnitudes across the field don't have any vignetting from the Sonoida data because it's very small postage stamps across the entire field. We compare that then with the APASS equivalent images of that field, the equivalent photometry for that field, and we model that as a surface fit, and we apply that to the entire image. We do that for all the images. So it's a way of sort of modeling, of removing the geometric effect. But it's not the best way to do it. It's just a crude way that I came up with to handle the 500,000 images in the survey. Okay. It really does need to go back and be resampled. That would be the better way to do it.
Anybody online with a question? Not now? Anybody in line? I have a question. You mentioned the kind of neat idea of monitoring Polaris in the daytime to help unravel that almost exactly 4-day period. I'll bet there are a whole lot of pitfalls to work around with daytime photometry to a few hundredths of a magnitude. Can you elaborate?
Actually, it comes back to the Betelgeuse thing. It actually has been done for that star and with that kind of precision, and so it can be done. The main thing you have to worry about is shading everything so that you don't get scattered light into your system. But luckily, Polaris is way north, And so it's easy to shade it in comparison to something like Betelgeuse, where the sun comes close to it, things like this. So it's actually probably the easiest target to do for daytime observing that I can think of. You can't miss it. You can see it, with a pair of binoculars in the daytime without any trouble at all.
And that fourth magnitude comp star,
Yeah.
you can still pick it out in the daytime.
Yes, you can. You can generally, with daytime observing and with sort of B and V filters, you can probably go down to about 6th or 7th magnitude with typical amateur telescopes. I wouldn't count on going much fainter than that, but you can certainly do that. And so anything that's 6th magnitude is pretty easy to do in the daytime. I've done a lot of this stuff in the near infrared, where the sky is daytime bright all the time. And, we can observe as faint as you want to go. You just have to gather a lot of data. But that's what you'd be doing with this.
Huh. Okay. As part of your APASS follow-on work, you mentioned a need for help with the setup daily at the sites. Does that mean the person needs to be physically near where the instrument is?
Oh, no. Everything is done remotely. What you need is to be able to start the system up, shut the system down at the end of the night, make sure that the pipeline gets enabled and things like this. So it's just sort of keeping an eye out over everything. But it's better to have a human involved in doing that than it is to assume that the software is going to be doing things properly. One of the things that's important is clouds. And so most of these sites have an all-sky cloud monitor. And you can look at that and at least mark down when you think that there are clouds going by. You use a Boltwood sensor, which are at all the sites, to further indicate how many clouds are up. Because one of the important things with something like APASS is you have to be able to do all-sky photometric calibration, which means you have to have a photometric sky. These telescopes are all put in photometric areas, but they only get like 200 nights a year that are photometric. The other 165 are not. And you just have to be able to identify those.
Right. You had mentioned the a(d) component that you said had been resolved by Hubble. Might that be a useful target for our speckle interferometry gang? Happen to remember separation?
I don't know the separation or the magnitude of the smaller star. So you would have to look that up. I don't think you can do it with speckle. I mean, it's probably, in the tens of milli-arcsecond separation. And maybe you can do that, maybe you can't, but, again, one of those things. Try it and see.
You'll never know if you don't try. Okay, anybody else? Yes, 2.
And just a quick bizarre question. Has anybody tried downloading large amounts of data with SpaceX satellites?
I don't follow that.
Well, yeah. Essentially.
Okay. Just, you mean Starlink or something like that?
Yeah, sorry, I should have used the noun, yeah.
Okay. Starlink is sort of 5G capable, I think.
Is that right, though?
And so you could do that, but usually on almost all satellites, they're asynchronous so that the upload time or the upload speed is less than the download speed. So you just have to watch it and make sure that you could actually do that. And they also may do data throttling if you're a site that's doing lots of data transfer. So somebody who's familiar with Starlink is probably a better one to ask on that. And I see a hand being raised over there. But I still think for image transfer, if you can do it through standard internet, that's great. And if you can't, then do the sneaker net. way of doing it. There's usually some operator that's at the facility that your remote telescope is at. They don't mind swapping out a hard drive and sending it back to you, FedEx or UPS. And that's a lot cheaper.
Yeah, actually, I think there's some good news with Starlink. I've recently got that myself, and I am seeing up to 300 by 300 megs per second at best of time day. Now, there is big variation in that, but certainly at quieter times of day, locally seeing some very high speeds, so it's a possibility.
Yeah, and the thing is that, you can do this offline. I mean, whenever the data rates are highest, then you can use those.
Yeah, Arne mentioned being involved in a lot of different projects, and I too have done several projects, one of which was the site selection choice for what is now known as the Vera Rubin Observatory. And one of the reasons that it's in Chile rather than Mexico had to do with data rate. We found that they didn't have optical links into the observatory in Mexico, whereas Chile is all fully developed and so on. And we were looking at storing or saving or archiving or whatever a terabyte per night, which at that time was horribly daunting. And the only way you could afford to do that was with FedEx or UPS or something like that, physically transferring stuff. Now, a terabyte in the course of one night is just nothing. It's just a totally different situation. We could have gone to Mexico and they would manage.
So Arne, on the Polaris project, if you can get a 4-degree field of view to work the brighter star, at that point, do you have to include extinction in your CCD/CMOS photometry?
Yeah, you do, and it depends on how far north you are. The
Yeah.
further north you are, the lesser that's an important quantity. And the thing is that, in your 4, 5, 6 hour observation, it really doesn't move that much in the sky. But if you're down at 30, 35 degrees latitude, it's a very different situation.
And I guess one more thought, is there any way to get free Starlink access for APASS as a way for Elon Musk to keep making up for all that he's done to astronomy?
There's a winner.
So when you said the sites upload star lists, do those include like a small image of the aperture for around that particular star, or is it just numbers of this is the magnitude at this time?
It's just the magnitude at this time. You're dealing with about 5 million objects per night off of one of these surveys.
The reason I was thinking about Kepler and TESS, which would do these postage stamps, around an image kind of thing, and then a stack of those.
We could certainly do it with the Bright Star extension, because that's only like 5,600 fields, and you've only got 9,000 plus stars that are down to 6 magnitude. And so it's something that you could easily do postage stamps around those and ship them back. But we found it not to be as effective as just transmitting the star list and then doing off-site analysis of that data. And then if you see something unusual, then you flag it, and then when the images come in, you can correct it then.
Just a note on the Starlink. So I'm in a new remote observatory about 10 miles east of San Simeon, in Central California, and it's called Skies Away Observatory, Brian Cogdell. And we were using a 30 megabit WISP because it's out in the middle of nowhere, so there's nothing out there. And recently changed it over to Starlink, and it's working quite well. We have about 6 instruments. Some of them are running these 60 megapixel, not QHY, but the ASI 200. So, and it's working quite well.
Going once, twice. Arne, thank you very much. And for those of you who want to make yourselves known regarding APASS or Polaris,